Hello, welcome to this session on using R for environmental economics. I'm grateful to the South Asian University for this invitation to participate in this conference. I'm Vikram Dayal and I work at the Institute of Economic Growth in Delhi. My co-author M. Rahul works in the Indian Economic Service. In this session, we'll look at several examples in environmental economics. Some to do with forests, some to do with pollution, and also what is very topical and should be very interesting, looking at the biologically invasive coronavirus. Now, these different examples use various research methods. We hope also to indicate, and more so in the paper, various research methods which are following a certain trend. So, there is a trend, for example, in economics of taking causal inference seriously. The Rubin causal model has been very influential, and we will look at the associated methods of experiments and matching. There is also increasing use of statistical inference, so we will also see how we can use simulation to understand statistical inference better. And finally, we will see how we can simulate in R various dynamic equations. So this comes in when we are trying to model biologically the spread of biologically invasive species. Currently, this is of interest because of the pandemic. Now, in this session, the focus really is on R and how you can work with R. It's just to show how R works, and we start from a very beginning, and we hope to give you a sense of what are the core methods that can be used repeatedly. To work in R, it's very important to get a good grasp of vectors. That gives you a basic intuitive feel for R. Then, if you are going to use R for data analysis, you naturally have to get comfortable with data frames. Much of the time will be spent working with relevant data frames. R is excellent. Much of data analysis, the time spent with data is really in preparing the data, wrangling the data. But also one can use graphs both to understand the data, to get insights that are close to the data, as Angus Deaton says, but also to communicate your findings. Not only to a broader community, but to fellow researchers, and as Andrew Gelman has pointed out, to understand your data analysis yourself. We'll have a brief look at how we estimate models through the formula interface in R. And finally, we'll try to show that a little bit of for loops goes a long way. Neither my co-author nor me have a detailed knowledge of programming. But through for loops, you can do simulations which are both statistical, giving you insight into statistical inference, understanding, and also give you a way of assessing statistical methods. Also, through for loops, you can simulate dynamic equations. So that's it. We hope that as an overview, we hope that you will find this session useful and interesting. Right. So now I'm going to show you how we can work with R in R Studio. When you open R Studio, you'll see these four panes. So this is the script window. So suppose I type 2 plus 2, it will be recorded here. This is the console. So I could directly enter 2 plus 2. This is where the output will be displayed. So I get 4. I could also do this. I can do run 2 plus 2 and then it's going to give me 4. Now here we see right now the environment is empty, but any objects created will be shown here. Suppose I tell R to create a scalar x with the value 2, and this is the assignment symbol in R. So I do run here. So I'm using this run. So I'm going to run this line in the script over here, and it creates this object here, and we see that the code is also registered here, but it hasn't printed it out. If I do this now, I get that x has a value 2. Now here I'm going to be talking about scalars, vectors and data frames in R. So we're going to really begin from the start, but hopefully, as you'll see, we'll go to more advanced applications soon. But this builds the foundations just in case you're new to R. Also, we'll do it via this very simple example of timber harvest in the textbook by Tittenberg and Lewis, the 2018 edition. So that's a script file, but R also allows you to create a variety of documents, R Studio. So one kind of document is an R notebook. So you can keep notes, you can integrate text, output and code in an HTML file. It also makes it convenient uh, to show how R works. So I'm going to go to view panes zoom source. So instead of all the 4 panes, I focus on this. So here we can focus on the code and the output. So this is a very basic starting point model for timber harvest. It's also a good entry point into resource economics. So here we will use a discount rate of 0.02 or 2%. So if I now run this, so I'm telling R, assign the value 0.02 to this R, this object R. Then I say multiply that by 100. So then I get an output of 2. Now in this, we're going to focus on the biological growth and how that determines the harvesting of timber. So just to keep things simple, we take the price as given, but obviously how prices evolve or how prices are expected to be will play a role in when to harvest. But for the time being, this is just one fixed. Now if I feed this into R and then I do price, this P is uppercase, this is lowercase, and we'll get an error. Now initially when you work in R, you often make errors and that can be frustrating, but one learns through these errors actually, and then over time one recognizes what is happening. If I now use the correct uppercase, so you can see I've got 1. Okay, now I feed this vector. This is going to be all the different ages. So this is an example from the Douglas fir forests, and these are the ages of timber, different ages at which in years at which we may consider cutting it for timber. It goes from 10 to 135. We feed this into R, and so you can see it's been fed in. We can extract different elements of this vector age with square brackets. We do 1, 2, 3. So this is asking R, please provide or print out for this vector the first, second and third. So 1:3 is first, second and third. So that's 10, 20 and 30 years. We could choose the second, fifth and seventh elements by, so now within these square brackets we provide this vector second, fifth and seventh. And the vector has parentheses, but this is square brackets. So just remember that. So we get 20 years, 50 years and 68 years. We will now input the corresponding volume of timber in cubic feet in this vector corresponding to those ages. So this is the relevant these are the relevant numbers, and now they have been fed into R and printed out. We will calculate the discounted value of the timber when you sell it by harvesting it at a certain age. What you will get by selling it is the price times the volume, but this will be at some point in the future, and in the case of timber it may be very far into the future. So this is what you get discounted by, so this is 1 plus R to the power of age. So this gives us the discounted value. Now the cost includes the planting cost and the harvesting cost. The harvesting cost is done at a certain age, and so this is the harvesting cost. So this gives us the profile of costs. Now the net benefits are simply value minus cost, so we can print it out like this. So this is the net benefits printed out by R. We can use the maximum function to choose that element of the net benefits which is maximum, and that is this. Now we are really interested in seeing how the net benefits vary with age. So what we do is we create a data frame called forest underscore data with the data.frame function, and within that we include these variables we have created above: age, volume, value, cost, and net benefits. Now we can see the top 6 rows with this function head, and this is the data frame. So here we have the top 6 rows. There are of course more rows in this. So we have net benefits, cost, value, volume, and age. Now that we've created this data frame, we will use the tidyverse package to plot the data. So first we will install the tidyverse package. We can use this function, or there is a tab in the RStudio icon. We can run this code install.packages. This has to be done only once. You install a package within RStudio or R only once. Thereafter, in every session that you use that particular package, you need to load it with this function library. So library is the name of the function, tidyverse is the package. So this is a very versatile package which has several other packages within it, made by Hadley Wickham, and it is now very highly downloaded and used. Now we will first want to see, we already use this function to see what is the maximum net benefits, but we want to see the associated information, what are the other variables, age, etc. especially. So we can pass this object, this data frame, with this percentage greater than percentage. This is called a pipe operator. It is saying take this data frame and then filter this so that net benefits are maximum, that row in this data frame where the net benefits are maximum, give us that row. This is equivalent to this line below, filter, use this data and this thing. The advantage of using this is that you can chain different commands. So when you're working with data, we will see later that this is quite useful. Both of us give us the same output. So this is the second command. It is giving us that row 1189 we saw is where it was maximized, and this is from the first command. We get the identical same row. So in R, of course, there are many ways of doing the same thing, and what we will largely follow is the tidyverse approach. This is ggplot. Gg stands for the grammar of graphics. We are now going to plot from the forest data frame, on the x-axis the age variable, on the y-axis the volume variable. So this creates the coordinate space. Then we tell R we want this geometric object. So geom underscore is the geometric object. Which one? A line. And then we have this parentheses. So when we do this, so we get this graph. This is summarizing the biological growth of timber, how the volume. So in as is quite common in biology, initially it picks up and then it tapers off. But you can see this is a long-lived process, slow growth process. This is about 100. Now we can ask for a plot of the net benefits. So instead of volume, we take the discounted net benefits, right? So this is where the discount rate comes in. And we see that below this age, so this is the zero line, it doesn't pay at all. Above this age, you can get some net benefits. Those are maximized at this age about 68. And then it starts thereafter dropping. So this would be the age if you are interested in maximizing timber harvest. Now in the Tittenberg and Lewis textbook, subsequent to this presentation of this numerical example, which is an entry point, they discuss various extensions to this basic model. One notable extension would be where you don't look only at timber. After all, the forest provides you with other things also. But this is a good entry point. And for our purposes, we've introduced via this example the basic starting elements of our scalars, vectors, and data frames. So vectors will give you, getting a good grasp of vectors gives us a good intuitive feel for how R works. And data frames are very important for any kind of plotting that we do and when we work with data. I'm now going to talk about some basic data analysis with R. And I'm going to use an example in a PLOS 1 paper which came out. The authors are Zano and co-authors. This is on health information and the choice of LPG in Rajasthan. So we all know that the indoor air pollution is a major issue in South Asian countries, so and in the developing world. So LPG is a cleaner fuel, and if you give as a treatment a certain health information and messaging, does it make a difference to the willingness to pay for LPG? Now, in what follows, I am only selecting from the paper. The paper itself is much richer, but the idea is to extract from the paper some key results and to illustrate basic data analysis with R. Now, Hadley Wickham is the author of the Tidyverse package, and he has been expositing this data analysis workflow in his work. So he's been writing about the data analysis workflow and also has designed Tidyverse so that you can conduct the entire data analysis workflow. Now, what are the stages in the data analysis workflow? In any data analysis workflow, first, read in the data. Second, wrangle or work with the data. Third, you graph the data. And fourth, you fit models to the data. Now, typically, of course, one need not go so sequentially, but it's useful to think of it that way. Now, like I said, we'll be looking at this paper on the effect of health awareness in the choice of cooking fuel in Rajasthan in India. The authors use an experiment in the field research design to study the effect of health awareness on the choice of cooking fuel. They conducted a survey of 544 households in rural Rajasthan in the Bikaner district. So we first read in the data. So we will first load the tidyverse package. We will also load the Haven package. Now the thing is, the data that is provided by the authors on the website of the open access journal, PLOS ONE, is the willingness to pay for WTP underscore LPG dot DTA. This is a data file. So I want to read this into R. So how will one go about it? You use the read underscore data function in DTA function in the Haven package. So this allows you to read data files into R. Stata is a much used package in economics. So therefore, many authors will publish their results, or the data will often be as a Stata dataset. We can now look at the data. And so because we are using the Haven package, it will provide a selection of rows and the first few columns. And then if you want to see more, you can click here and you can see the other columns. Now this happens of course in the HTML, so you can see the entire data set. It's quite convenient. We can also use head, which we had seen earlier. This would give the top rows printout. So if it's a document, you can print it out in that way. Another way of looking at the data is to use the glimpse function, which is a tidyverse function. So please note that when we read in the data, we create this data frame within our WTP underscore LPG. So we use the glimpse function, and this gives us a different kind of view, which is also useful. It gives you each variable and the type of variable and the observations on it. You can also use the str or structure command in R. So this would work outside the tidyverse package, what is called base R. So base R is R without any packages. Now the next stage would be wrangling or working with the data. So we take the data frame, and we had discussed this pipe operator. So this is essentially chaining together a series of actions. So first we take the data frame, then in this data frame we select these two variables, W2P underscore LPG, which is the willingness to pay for LPG, and the treatment indicator. So one is the treatment group, I think, and 0 is the control group. So basically it indicates the which group, treatment group, the household belongs to. Having selected these variables, we then do na.omit. So we omit all observations for which data is missing. We then subsequently group by the treatment indicator, treatment group indicator, and then we use the summarize function. So we calculate the mean willingness to pay, which is the mean of WTP underscore LPG, the willingness to pay for LPG. So we get the mean willingness to pay by treatment group. So here we can see that they vary. So for the control group, the mean willingness to pay is rupees 351. For the treatment group, the mean willingness to pay is 361. We can plot the data now, the next thing in the workflow. So we will use the ggplot function in the tidyverse package as we did before in the basic forest example. This is the name of the data frame, WTP underscore LPG, and then we say within this, this is for aesthetic. So we tell our what variables, so we want willingness to pay for LPG on the y-axis, and we want the treatment to be on the x-axis plus geom point. So then we get this figure. So we can say that see that this is the willingness to pay in the control group. This is the willingness to pay in the treatment group. Now the thing is the this there are a lot of overlapping points. So in this case, and this is a practice which one can follow also in Stata, to make scatter plots more informative where there are overlapping points, we use the jitter function. So we can refine the plot above so that we can get more insight from the plot. So we add geom jitter and we also add a smooth. So this is basically going to fit a regression line, and this is going to add some random noise to each observation, each point in the scatter plot. Now you can see we've added this line, so you can see it's just slightly. So this, as we saw earlier, the mean is a little higher in the treatment group. It's about 10 higher. So from 350 to about 360 the line is going up. But this also gives you a more effective, so you're seeing the underlying data points essentially. So there is one outlier, there is a few outliers here. And then you also notice that there is a rounding off. So you ask people for the willingness to pay. So there's a rounding off. So you'll find there are more observations at the 400 than, so people kind of round off, and then you can see there's a pattern here also. So this would be 350. This is 350. So although it's continuous, people have a tendency to give responses which are close to say 350, 400, like that. Now we will now create dummies. So in R, one uses the factor function. Now we had treatment, which was for purposes of drawing this scatter plot. It's actually a categorical variable, but when you draw the scatter plot, you want the points to be there. Then it has to be treated as a numerical variable. But in the regression, we want to create a dummy. So we simply do factor treatment. So we will generate these variables. So this is the name of the data set. So we're saying, okay, we create a new data set. It's the same as the old. So we're just adding this variable to WTP LPG. So we take this data, and then in this data, we create, mutate is simply creating a new variable, and we call it treatfac is equal to the treatment variable, but now we treat it as a factor. And we do this for the variable male. Okay, male is 1 and female is 0. And then we also create a, an interactive variable. So male times, we are interacting male and treatment. So that's now done. Now we will proceed with fitting models. Now in R you could simply do LM. This is your Y variable, this is your X variable, and then this is the most basic command for a linear model in R. And regression models, essentially build on this basic syntax. So LM is linear model. Now we can create an object mod 1a, which would, and then what we can do is extract information from mod 1a. So first we create this object, which is the object in R corresponding to the linear model which we have specified here, and then we can ask for it to be printed. Now when we ask for this, we will see that the first command will give us a very bare and minimalist output, and the second, so it's too little, and the second command gives us too much, flooded with too many things. So let's do this. So this is the output that you get from the, so this is mod 1a. So we're told, okay, this is the intercept 351, and then the treatment group. So this is something we'd already seen in the conditional means. The summary command adds much more, so you get information on the residuals, the coefficients, t-values, so etc. etc. A better way to proceed is to use the TechRec package, and it's useful to use this even when one is uh, uh, working with the data, even before one is writing the output, because it just isn't very difficult to use and you can see what's happening and it's much cleaner. So this is the same as before. We call this mod 1a and we call this mod 1b. So it's the same linear model that we used before. This is willingness to pay on the treatment. The data is this thing. Now we add the interactions. So we have the treatment variable and the mail variable, and then the interaction of the two, and the data set is the same. So this is mod 1b, this is mod 1a, and then we use the screen reg function. So we want the two models to be so we use this syntax. We want a table which will contain these two models, and then these are some options which for the time being we'll not worry too much about. And you can see we get a very nice output. So even when you are in the stages of working, it's useful to see the output like this. So in this model where we only use the treatment variable, so this is just the difference of mean, so we get this 10, and the confidence interval goes from minus 1.79 to 22.26. So our coefficient of interest is really this. And then when we in this we see, okay, we get something similar. So this would illustrate some basic data analysis in R, and we can also, these days in economics we use, this is almost standard to use robust standard errors, so this can be done with the estimator package, and then the rest of it is pretty similar. But so here we started with the data, we read it in, let me go back to the workflow and then just to recapitulate. We read in the data, we wrangled and worked with the data, we graphed the data, and we fitted models to the data. So we'll now look at some wrangling and graphing of data in another study which uses an experiment in the field. Wrangling and graphing data go well together. In order to graph data, we need to work backwards the graph we have in mind, and then wrangle the data so that it can be graphed in the way we want. I will illustrate with this important study by Duflo et al., published in several papers and a report, on the impact evaluation of an environmental audit scheme in Gujarat, India. There are informational asymmetries between regulated industrial plants and the environmental regulators. In this study, the control group were those where what was true before the study continued. They were audits by third party auditors paid by the under regulation firms. In the treatment, which was randomly assigned, auditors paid from a central pool of funds rather than by the firms were employed. Out of 473 audit eligible plants in Ahmedabad and Surat, 233 were randomly exposed to the new system, and the remaining in the old system acted as the control group. So, in the control group, the firms basically choose their auditors but not in the treatment group. And back checks were organized in 20% of the audits, both in the treatment and the control group. So, the auditors went in, measured the pollution, and later independently there were 20% of the plants, some independent measurements were made. Now, graphs bring out key aspects of the study. It is best to visualize the graph you have in mind and work backwards. Also, remember, as Andrew Gelman has said, that all graphs are about comparisons. So, let's first go to the graph we have in mind. This is a graph in one of the papers. It's a version of the same graph that is there in one of the papers by Duflo et al. Coming out of this study. It's not exactly the same, but in essence, it is the same. So, in this, we are going to plot the distribution of pollution. And we choose density curves to do so. These are smooth histograms. We put in a vertical line for that level of pollution, which is the pollution standard mandated under law. We arrange these density curves. So we do this by 4 categories: 2 of this variable and 2 of this variable. This variable is the audited recording of the pollution. So these are the reported pollution levels reported by the auditors. These are the independent checks. In this category, we have the control group. In this category, we have the treatment group. So, we have in mind, we would have some idea, we have these variables in our data, and then we visualize that we would like to have this plotting the density of the distribution by these 4 categories. Now, we would not know in advance precisely what shape these would take, but we will have a sense that these are the comparisons we want to make. And then we work backwards and do the wrangling of the data and the entering of the data accordingly. So first we load the packages, tidyverse, Haven. Haven allows us to read Stata files. We use the read underscore data. This is the data in our computer, and this is what we call it. Now we use the glimpse function to have a glimpse of the data. There are 6782 rows and 26 columns. We'll be focusing on the treatment control or not. We'll be control for, and this is the density that we want to plot the distribution of this, and then we have back check or not, 0 or 1. We will use a data verb called mutate, which helps us create new variables. Also, the factor function will be used, which tells R that a variable is categorical. So our first task is so the treatment variable is 0 and 1, so we convert it into a factor and we recode the zeros as control and the 1 as treatment. So we have a new variable treat. We do the same with backcheck. So we create a new variable back, and this is a factor version of backcheck. and we recode 0 as audit and 1 as backcheck. We will now employ the data verb filter. So this helps us select rows fulfilling a condition. So we take the data and then we filter for the rows that we want. So we're going to be focusing notably among these conditions is the parameter should be suspended particulate matter and boiler should be this type of boiler. We will now use ggplot, which is a plotting function where gg stands for the grammar of graphics. Geom is the type of geometric object. V-line gives us a vertical line, and facet grid helps us create a grid with columns and rows of two variables. So we use this, the pipe operator. So we are saying take this data, then use the ggplot function, and we want x to be the pol variable, that is pollution. Draw a geom object, which is the density curve of this for the distribution of this variable. Add a vertical line at 150. This is the standard for pollution. Use a dashed line type and then create a grid. So we want conditional distribution of pol with respect to the two categories of treat and the two categories of backcheck. And we get our figure. Now this is a key figure showing a key insight, and this would perhaps be possible to know anecdotally from the stakeholders. So it is suspected that this is in the old system where firms choose the auditor will be unlikely to want to displease the firm. So let's say there's a plant which is having this level of pollution, right? So this is just above the standard. So the auditor will have an incentive to report the measured pollution as something below, slightly below the standard. Thereby, there will be no action against the plant. And this is this idea that when the firm chooses the auditor, there's this possibility is also borne out by the comparison with the treatment group, where the firms don't choose the auditor, and we don't see this, this spiking before. Another way of looking at it is to compare with the back check. So we see the marked contrast between the audit and the back check here. The contrast here is much less compared to here. Now that we've seen one of the key graphs, we can remove this object because then we will be working with yet another data set that the authors provide. So we use the rm function to remove the object. Now we will read in the data. We use the filter verb, so we take the data, we filter, and now we will be looking only at the control group. So we have all these conditions. We once again create categorical variables. So this is the plant ID. So each plant is uniquely identified. Each auditor is uniquely identified. We can use the estimator function to do a linear model with robust standard errors. So what we are trying to do is that in the control group, the auditors carry out certain checks, they report certain levels of pollution that they claim were the observed levels of pollution. Now, the authors here are investigating auditor heterogeneity. So the idea is that auditors vary in quality, and you can measure the accuracy of the auditor's reports by comparing with independent checks that were done. And that is this variable diff. So the difference between the auditor's readings and the independent checks is a measure of auditor accuracy. Now what we do is we do this, and the reason why we're doing basically a way of getting the means for, we want to compare the means of the readings by each auditor. So we regress these auditor accuracy as measured by the difference on dummies for each auditor. This is simply a region dummy for Ahmedabad and Surat. Then we use the broom package, but basically what this will do, basically we get in a data frame our different estimates and our standard errors. We then use the arrange data verb, which arranges the estimates. These estimates are actually better called auditor accuracy, so we rename them with this rename function. And then we also create a new variable rank equal to 1 to 17. So now we have created this. These are all the auditors. This is the coefficient of the auditor accuracy, and these are the standard errors. So now we can use ggplot as before. This is the data set. This is what we want on the x-axis, that is the rank. So rank in terms of auditor accuracy. On the y-axis, we have auditor accuracy. We use geom point to represent the mean, and then we use error bars for the lower and upper confidence levels. We add a horizontal line for 0, because if diff is 0, that means that auditor is accurate, and we choose line type equal to dotted for that. This also corresponds to one of the figures of Duflo et al. In one of their papers. So we see that there is considerable, so these two auditors in mean are the same. If you compare this auditor and this auditor has a much higher variation in the readings. These other, so these are the most accurate, and then the accuracy is going down. This is the most inaccurate auditor. And then the confidence interval gives us a sense of how variable their readings were. So the argument is that there is considerable heterogeneity in the auditors, so they vary in quality, and anecdotally also the authors report that this is well known among the stakeholders. So this is also a key figure in the paper. We now move to our third figure. So we'll remove the data and the associated objects we have created. We read in the data. Now once again we use filter. There are certain conditions. We create some new variables, primarily changing these variables to factors. Then we use the group by. So group by basically helps us to group by a certain variable. So we are going to group by the treatment group, the parameter of pollution, and whether backcheck happened or not. And then we will, for each of these categories, we will calculate the mean level of pollution. So here we have the mean level of pollution. Here this is the control group, this is the treatment group, this is the parameter BOD, this is SPM, this is backcheck 0, 1. So you can see for all these categories we have the mean level of pollution. Now we will plot, make a bar plot. So color in ggplot is the color of the geometric object, fill is the color of the fill used in the geometric object. On the x-axis, we have the treatment group. On the y-axis, we have the level of pollution. And then the color is backcheck or not. And also we wrap. So we will have facets for the kind of parameters. So we have different pollution parameters, TDS, etc., BOD. So we have three categories of types of pollution. So on the x-axis, we have the treatment. So here treatment is, this is the control group, this is the treatment group, this is the control group, this is the treatment group, and so on. So we have 6 of these bars. This is on the y-axis, we have the mean of the pollution of the readings in that category. This is the reddish is 0 and the turquoise-ish is 1. So this is no back check, this is with back check. So this is the auditor reports. So you can see that for BOD, and these are the 3 parameters of pollution. So this is types of pollution. This is BOD, this is suspended particulate matter, and this is TDS. So over here you see that in the control group, there is quite a lot of underreporting of the pollution. We have underreporting here also by the audited reports. The back check is higher, but the gap seems to be lower between the, so this is the gap between the back check and the audited. So this gap is lower than this gap. With SPM, this gap is really much lower than this gap. And finally, with TDS, once again we have a slightly lower gap and we have much more underreporting in the control group. So these 3 figures capture key aspects of the study. The authors made an argument for changing the way audits were done by using a different method to assign auditors to firms. So far, we've seen 2 experimental studies, one on the adoption of LPG, another on auditing of pollution in Gujarat. We had begun with the best time to harvest timber, but that was the case from Douglas fir forests. We will now look at the issue of forest management in Uttarakhand. So, what effect do state managed forests versus village council managed forests? What is the difference in performance of these 2 different ways of managing forests or these 2 different institutions? This is a paper by Somanathan et al., which appeared in PNAS. Now, tropical forests were largely nationalized during the colonial rule. Then in 1930, in Uttarakhand, after long protests, council managed forest areas were allowed. So the question is, have been the long-term consequences? So did that result in lower ground cover? Are village managed forests more cost effective? As far as costs go, and the authors have systematically compared the costs, they reach this conclusion. I quote, the cost of administration in state forests is more than 7 times as much as in council forests, reflecting the absence of bureaucracy in the councils and also their greater flexibility in hiring watchmen. So after costs, they come to the question of how do you of comparing the ground cover. Now we need to take into account the allocation of lands to state and village council managed forests. So, from historical evidence, the authors show that state forest lands at the time of village council managed forests being allowed, so the state forest lands had more cover when these decisions were made. The authors have collected data on 217 villages and adjoining forests in 10 different areas. The bottom line of the paper is that village council management costs an order of magnitude less per unit area and does no worse and possibly better at conservation than state management. So, the second part of this is what is established uh, through comparing the state and village council managed forests after accounting for some key covariates. So, the authors have used very carefully gathered data, satellite image work, on ground survey, etc. The matching method was also used, and we will focus on that over here in an illustrative way and also intuitively using graphs. So, these are the variables. We want to compare the crown cover between village forests, which is 1 with the village forest dummy, and state forests, which are 0 in terms of the village forest dummy. Then we have these three variables which have an effect on the crown cover: aspect, population density, and neighboring stock. We will look at the issue of balance. So, what matching tries to achieve, it looks at observational data but through the lens of what we try to do when we use experiments or randomization of treatments. So, we want the treatment and the control groups to be very similar along relevant covariates. Of course, with observational data, you can only look at the covariates for which you have data. Now, three key covariates are aspect, population density, and neighboring stock. So, we look at this trivariate balance. So, we use ggplot. This is the x, y, and we convert different ranges of neighboring stock into a factor. So, these will make up the facets. And then we ask R to plot points in this space. The points will be colored according to the village forest dummy. So here on the x-axis we have aspect, here we have population density, here we have through color the village forest dummy. Then we have each facet showing a range of values. So over here neighboring stock goes from this value to this value. Over here neighboring stock goes from this value to this value. So essentially the idea of balance is, so we see these two blue dots or turquoise dots, let's say they're blue. So there's no red dot close to it. Similarly, you have these red dots and you have no turquoise dot close to it. So Gary King says matching should more appropriately be called pruning. So in matching, you prune the data so that you have overlap between the treatment and control groups in terms of the covariates. In R, there are several packages that can do matching. One of them is match it. So we would have installed this and then we load it. Then we use the match it function. Here we have the treatment variable vfdum. So this shows the treatment and control group. So we want to match the observations between treatment and control with respect to aspect, population density, and n stock. The method we will use is coarsened exact matching. So exact matching, say, would be, suppose we're looking at years of education. So many years of education, so many months, and so many days. So getting an exact match would mean that, let's say we've got years and months and days of education, so we exactly match the treatment and control observations on the exact number of years, months, and days that the person has received in education. However, in coarsened exact matching, since that is not really feasible with continuous variables, we can coarsen the exact matching. So we can say we can have more natural ranges, like up to class 12, then from class 12 up till getting a bachelor's, and so on. So that's the intuitive sense of coarsened exact matching. The more formal case for this has been made by Gary King and authors. Now, when we use this matchit function, we will have this object which is created. We then use the match.data function, so we plug this in over here, and this will be the data frame post matching. So essentially this is the data frame with the pruned observations. We can look at variable by variable the balance, so we are keeping things simple also, and these, in this case, these are the three key variables. So we can look at the balance in these between treatment and control with respect to these three variables, one variable at a time. For this, there's a package in R that we will use called Cobalt, and we will use the loveplot function. This is the object that was the result of using the matchit. So this is this object, so we plug it in over here. This produces this. So you can see this is the standardized mean differences of these three variables between the treatment and the control group. This is the data which is after matching. This is the data in the data set before matching. So you can see that matching has led to an improvement in balance in this case. We can also look at the trivariate space, and again you see now you will find, so for example there's these two colors, they're pretty so they're dot points with these two colors close to each other. Over here there's a red which is just below this, and it's possible to see it here. It may not be possible to see it from here, but you can see it in my laptop. Here again you see they're almost on top of each other. So there is balance even in the trivariate space. Gary King argues that the purpose of matching is to reduce extrapolation beyond the support of the data and to reduce model dependence. Model dependence is simply the phenomenon where the coefficient or the quantity of interest that we estimate varies a lot depending on which specification we use, which regression specification or what model we use. Now in this case, in models 1 and 2, this specification is the same as this specification is the same as this. Models 1 and 2 are with the data prior to matching. Models 3 and 4 are with the data after matching. So before matching we have 582 observations, after matching we have 322. So this is what Gary King says, matching is pruning the data to improve balance. But you can see our quantity of interest is the coefficient of the village forest dummy. So here it is minus 5.63. Now, once we include population density squared as a covariate, this falls to minus 1.94. With the matched data, however, we find that the coefficient is minus 0.25 and here it is 0.03. So there is less model dependence. So to summarize, we use matching to reduce extrapolation beyond the support of the data. It's a way of pruning the data so that you have less dependence on the specification that you use. Right. In this snippet, we're going to look at simulation in R, how using for loops and a function can go a long way. We're going to first look at statistical simulation here, and later we'll see simulation of difference equations. So we can use a pack of playing cards just to make it intuitive. So we're really just getting some insights into inference, statistical and causal. We begin with random sampling from a pack of cards. We sample 3 cards with replacement. So the probability of any card being picked does not change. So this is sample 1, this is sample 2. Now can we do the same thing in R? So to get a random sample in R, we'll say, okay, this is the sample size. We use the sample function. It goes from 1 to 13 as is the value of a card. The size is equal to sample size, and we allow replacement to be carried out. So this is the sample that we've drawn. You can see 11 repeats. So allowing replacement to be true is like drawing from an infinite population. So in each draw, the probability of 11 being selected is independent. So it doesn't change with what. So each draw is independent of the previous one. So we load the TechRec package and we use this. So this is basically a regression way of finding the mean. So the mean is estimated in the sample to be 7.81. There are 16 observations here. Now the sampling distribution of the mean of the samples is what we now will try and plot and examine. So we draw a random sample of cards, we calculate the mean of the sample, then we store the mean, and then we repeat this process. Finally, once we've done this a number of times, again and again, we plot the histogram of sample means. This gives us the sampling distribution of the mean of the samples. So this is the sample size, this is the number of loops. We create a vector for the sample means, we create a vector for the samples, and then we start our for loop. The for loop has this structure: for open parenthesis I in 1 to loop num. So I will go from 1 till, and we've put 1000 here, so 1 to 1000. So I will be 1, then 2, then 3. So initially I will be 1. Then what is within these braces will be carried out. So we have x. So this will be the sample. We sample from 1 to 13 as before, and this is our sample. Then we go to the next line. So in x bar, in the first, now here I will be 1. So this is a vector of length 1000. So the first slot will be filled by the estimated mean of the first sample. Then it will go back. I will then be 2. We repeat this. So now the second slot will be filled by the mean of the second sample. We put this in a data frame. The mean is 7. So this is pretty close to the true population mean. Now as we've been doing, we use tidyverse, ggplot. We plot a histogram. So we geom histogram of x bar. So we see that, okay, this is around 7 is the center of this histogram, and it's varying right from here to even there's some observation which is equal to 10. So we know that the sample mean is uh, unbiased, which means that if we do it again and again, on average we will get 7. The sample mean is a unbiased estimator of the population mean. Now we do a hypothetical experiment. Let's say the value on a card varies from 1 to 13, this we know. And let's say that we have a treatment which adds 2 to the value of the card if the card gets treated. Now the causal effect is equal to the value of the card if treated minus the value of the card if not treated, and by assumption this is 2. Now in the potential outcomes framework, causal effect is just this, the value of the card if treated minus the value of the card if not treated, that's 2. And in the potential outcomes framework notation, or in the Neyman-Rubin causal model notation, the causal effect on a card I, the ith card, is the observed outcome, or the potential outcome, sorry, the potential outcome y of the ith card. One is denoting if treated. So we're just translating this into symbols. So some variation of this mathematical symbols are used in the potential outcomes framework. Minus yi0. So either yi1 is observed or yi0 is observed. So if it's a card which gets the treatment, then this will be observed. If I is a card that is in the control group, then this is the y that we will observe. So to illustrate, this is the control group. So here the treatment is not there. So whatever is this 4 will be the observed y. And here the observed y will be 7 and so on. So we will observe 4, 7 and 6, and we will observe that this is in the control group. What we will not observe is what the value of this card would be had it been treated. Similarly, in the treatment group, we have these numbers. These are the numbers which we would observe. So we are just making a strong assumption that in each case, exactly 2 will be added by the treatment for illustrative purposes. So here the y we'll observe is 2 plus 2 is 4, but what we will not observe is what the value of this card would have been had it been in the control group. Okay, so in this simulation experiment, we know we are fixing the value of the treatment as 2. So we draw a sample from a pack of cards randomly. We assign half the sample to the treatment group and half the sample to the control group. We estimate the effect of treatment on the outcome and store the value. We repeat and plot distribution of estimates. Now, if the distribution of estimates is centered on the treatment effect, right, then we know of the true treatment effect, which is 2, then we would know that random assignment works. Now we will use a function to do which incorporates a for loop, just like we did earlier. We had the recipe, we had translated the recipe into R code, but now we will go further. We will use a function within which we will put the recipe so that we can use the recipe over and over again. Now just to illustrate what a function in R looks like, let's say this is a function. We want to create a function divide by 3. So first, this is the name of the function. Then we put this assignment, we say function, and then we indicate what the inputs to the function are. So these are the inputs which have to be provided by the user of the function. Further, after this is what the function will do. It will divide x by 3. So this is created. Now once this function is created, this is given as an input by the user to R. So divide by 3. So once R receives this input, it divides 3 by 3 and gives you 1. Divide by 3, in parenthesis 100, and you get 33. So we've created a function which has this recipe. And then we can get from this function a data frame. This data frame has this. This is the estimate of the treatment effect. This is the p-value, the standard error. This is if it's significant or not. So we use ggplot and plot the distribution of these estimates, and we see, okay, it's centered on the true value too, but it does vary a lot. Now we go a little further, and this becomes interesting. So this is in a sense inspired by the work of Andrew Gelman, who has gone beyond type 1 and type 2 errors. He says what's more useful is to think of type S and type M errors. So type S is sign errors, and type M are order of magnitude errors. So here we know that the true value is about 2. So we saw earlier that there's a wide variation. But let's say there's this value around 5. So we see, yes, there are some values over here which are around 5. Now, the tricky thing here is not only is this very far from the true value, but because of its large value, the p-value is very low. So we would, I mean, typically as researchers, you'd say, oh yes, this is statistically very significant, and we tend to take that as at face value you normally. So I'm just pointing out the paradoxical nature of these p-values. On this side, we have type S errors because the sign is also wrong, but then again, these are statistically significant. So we would actually have more credible faith in these estimates than in these. But say if you compare an estimate here and here, this is insignificant, this is significant, but actually this is closer to the true value. So this implies that, okay, with a lot of noise, as Andrew Gelman says, if you have a lot of noise and you have, so noise means that there's a lot of variation in the data or there's measurement error, and with small sample sizes, then p-values can be misleading. So that's why in say in the PLOS One article which we had discussed earlier in LPG, people are often asked to show that their study has enough power. Now we do this. What if the sample size is larger? So here you can see it's going from below 0 to a little over 5. So this, firstly, the good news is that this, so we get less of these extreme. And the other thing that we notice is that almost with large sample sizes, often this happens. All the estimates end up being significant. And but once again, you could be a little distance from it. On this side, it would not be so statistically significant, but over here, say this is something beyond 3, so this is very statistically significant. But of course, with a larger sample size, the estimates tend to be closer to the true value. Of course, assuming that we have random assignment. Now, we could have the control group in an observational study. We could have systematic differences in balance. So this is something we discussed in the matching part of this video. So this just should gives it some intuition about that. So in the treatment group, we have likely to have more face guards. So the observed Y will end up being larger for two reasons. One is it's in the treatment group, and the second is that the treatment group has more face guards. So through matching or through regression, we can account or adjust for this part of the thing, that the treatment group and the control group have systematic differences, not just in the treatment assignment. We'll now look very quickly at dynamic simulation models for biological issues, and our idea is that we're thinking of the example of coronavirus. And nonlinear dynamics can be complex. Over here, we see the plot of x over time. So x is the process generating x stochastic or deterministic. So our instinct might be that okay, because it's going up and down a lot, it's stochastic, but it's deterministic. So if you know the previous period value of x, you know you can work out the exact value of the next period's x, of course, if you know this equation which has determined these values. So this is simply the logistic equation with a difference equation in discrete time. Coming to biological invasions, what do we mean by this? Biologically invasive species include pests and pathogens, so that includes the coronavirus, plants and animals which invade and take over ecological systems, harming the production of ecosystem services. Perrings et al. Have said that the problem of invasive species makes all other environmental problems pale into insignificance. And Charles Perrings is a prominent ecological economist who has studied infectious diseases and biological invasions. Now, epidemiologists, ecologists, economists, and ecological economists build on workhorse models of infectious disease epidemiology. So, these models can be traced to Kermack and McKendrick, and from their 1927 paper, this is the data. It's there in an R package. So this is the plague in Bombay from 1905 to 1906. These are weeks, so it goes from 0 to a little over 30 weeks. And these are the cumulative deaths. So initially, the deaths are slow, and then there's a pickup, and then it finally dies out. The plague died out. Okay, so we can do this simulation either of differential equations or of difference equations. Here I'll just show how we can simulate difference equations using for loops. There is a desolve package in R through which you can do the simulation of differential equations. So let xt plus 1 equal xt plus 2 and let x1 be 3. Then quite clearly x2 is equal to x1 plus 2 is equal to 5. We simply plug in the 3 here, so 3 plus 2 is 5. So we can iteratively get the solution. X3 is equal to x2 plus 2 is equal to 7. So we can numerically simulate a difference equation by iteration. This means we can use a for loop like we did in the earlier snippet for statistical simulation. So we'll do the same thing that we did in the previous slide through a for loop. Here x is a numeric with 3 spaces. It's a vector. We just create this so that we can fill in the slots. This is the initial value x1, 3, and then we simulate for the next 2 periods. So we use a for loop. I goes initially from 2. So here let's say I is 2 initially, so this will be x2 is equal to I minus 1. So this is x1 plus 2. Then it goes into I being 3, and so we get 5 and 7. So this is what we had got here. We'll just discuss a very basic, the most basic model, SIR model, and in practice people use more detailed and uh, more detailed models which fit the problem that they're trying to study. Here we're just trying to get some qualitative insight. So in these models we have divided the population into compartments. So here there's a susceptible compartment, then an infected compartment, and then a resistant compartment. And these three make up the entire, so n is equal to s plus I plus r, and people initially, the infecteds will be very low. People move from being susceptible to getting infected and then resistant. Now the basic thing, and we saw in the previous graph that there's this initial, so the cumulative cases kind of take that form, and we'll see the rate of infections will be like that. So the new infections are modeled as being equal to the product of the infected and the susceptible in the previous period multiplied by this parameter. So the idea is that how does the epidemic spread? And there is the contact will vary by the kind of pathogen and disease, etc. But whatever is the relevant type of contact, this contact between infecteds and susceptibles is what determines how many new people get infected. If the number of people infected is low, then the newly infected will be low. But after a while, this starts building up, so then this is multiplying this. Over time, more and more people will recover, and so this itself will then start falling, and the number of susceptibles also over time has been, so more and more of the population have moved to I and to R, so the thing dies out. So we set up by setting up all the parameters here, giving them values, and then we use this for loop, and these are our difference equations. So this is the difference equation for newly infected, this is the susceptible. So susceptible minus newly infected in the previous period gives you the next period susceptible. The recovered is just this parameter multiplied by the previous period's infected. This period's infected equals to last time's infected plus newly infected minus those who recover. So it's quite straightforward. Then we create this variable, we gather all the results in a data frame, and then we can plot. So it's important to be able to plot because that's what gives us the insight. So for those parameters we get this kind of thing, and we're looking at qualitative insight. So this is the proportion of people who get infected. So initially the rate of infection is the proportion of infected is low, and then it peaks at 0.20 in this, and then it finally goes back to 0 at about 100. Now one of the iconic symbols of advice on the corona pandemic has been, especially in the initial days, about the urgency of flattening the curve. So if you have measures, so we created a function, and this is just qualitatively. So suppose the beta is reduced by 80%, then the resulting curve is like this. So you can see the peak is coming at about 75. So the peak is delayed, and also there is a lower peak. So this is 0.20 at about 50, and here it's 0.12 at about 75. Of course, we can't take this is a purely qualitative exercise. It's numerical, but it's essentially over here giving us some very basic qualitative insight, notably the importance of looking at this uh, in terms of people's contact rate and flattening the curve. So we want this to be below the ability of the healthcare system to handle. Now this basic model is built on, and you can make it more detailed, you can add an exposed, so people don't get infected immediately, and that's one of the complications of the coronavirus. You can have people in two patches and mobility between patches, and you can see how things play out. You can make this detailed, include health infrastructure variables, and then non-specialists can play with different settings of parameters and see resulting scenarios. So get an intuitive feel for how things may affect something else. Now one thing one can do is to use a calibration approach, take parameters. So in the early days of the coronavirus, so this paper on Indonesia, for example, used a calibration approach. So you take parameters from previous experiences. So you kind of say, okay, a good guess for these reasons of for the parameter is this. Then, if you're a mathematician, you can say, okay, if the parameter varies between so and so, then you have these features of the system. You look at stability, see how the dynamics change as the parameters change, etc. You can use it for detailed predictions, and then of course either use a calibration approach or you can fit to data. Once there's more data, you can use likelihood or Bayesian approaches. Of course, the issue that economists will raise, and these are two growth economists. So, Charles Jones is a growth economist, and so they've attempted to address the exogeneity and measurement issues in particular. Measurement has been a key issue. How do you get the data on cases, etc.? One can also, like I said, use the DSolve package for simulating differential equations, and one can use dynamic simulation to look at other issues in ecological economics. So, for example, in my PhD, I studied the spread of the biologically invasive Prosopis juliflora in Ranthambore National Park using a simulation model. I'll now go through some of the key references. For basics of forest in R, that example that we discussed was taken from the Tittenberg and Lewis textbook 2018, Environmental and Natural Resource Economics. There's a book by me, Quantitative Economics with R, a data science approach, published by Springer in 2020, that goes through R, the style that we've used in this video, and uses a fairly user-friendly approach. This is a very good book. It's available freely online. It is would be a very good reference. Vikram and Grollemund are for data science. This is the paper by Zano et al. Health Awareness in the Transition Towards Clean Cooking Fuels, Evidence from Rajasthan, that we discussed in the basic data analysis. This is a review, a comprehensive review of the economics of household pollution. There's a Springer brief by me that briefly is a kind of brief and user-friendly survey of environment in economics and development. In the auditing pollution, we used several publications by Duflo et al. So this is the report, IIED, and this is available on the web. This is American Economic Review. This is Quarterly Journal of Economics. Essentially truth telling by third-party auditors. For forests in Uttarakhand, we use this publication by Somnathan, PNAS. So you can get the paper on the online. This is a paper on coarsened exact matching, and this is a more recent paper and saying why propensity scores should not be used for matching. So propensity scores are a highly used method for matching, and so Gary King and Nielsen have made an argument. And for cards and simulation, there's this wonderful paper. It deserves to be read by all of us, Misunderstandings Among Experimentalists and Observationalists About Causal Inference. It's both excellent and not too difficult to follow. Then there's this delightful book by Gelman, Vettari et al., Regression and Other Stories. So the type M errors, you'll find nice exposition here. For simulating ecological dynamics, There's a primer of ecology with R. You'll find a lot of resources. Uh, then there's this publication in 2020 by Perrings and co-authors, Mobility Restrictions for the Control of Epidemics, When Do They Work? This is an excellent short piece on biological invasion risks in the public good and economic perspective in conservation ecology. So, in this is an application to Ranthambore National Park in Rajasthan in India. So, this is about how an invasive tree could affect diverse agents in the land of the tiger. Now, one can explore the MDP toolbox package in R and the related literature. This is a growth area I foresee, Markov decision processes or stochastic dynamic programming. It's a growth area also because it's an area of artificial intelligence, a key area, reinforcement learning. So there's likely to be a lot of development of algorithms, etc. And then NLRX, it works with the NetLogo package. So this allows you to do agent-based modeling. Thank you.